This video will focus on two more types of displays for numerical data, the dot plot and the stem plot. Dot plots are really easy to make, really easy to read. They're good for large sets of data. One downside is that they're difficult to compare related sets. Stem plots not only give us a good picture of the shape of a distribution, as many of our graphs do, but this also includes the numerical values in the plot itself, which is kind of a nice feature. Stem plots are best for small data sets and doesn't work well for negative numbers. So we like a small number of observations that are greater than 0 to make a stem plot. Stem plots make it really easy to compare related sets as long as there are no more than 2 sets that we're trying to compare. Here are written instructions on how to make a stem plot. Pause the video, take a moment to read through these instructions and take notes. Then I will talk back through these on another slide when I actually have the stem plot in front of us. This table shows some of the data that I'm going to use to construct our first stem plot. As you can see, it describes literacy in Islamic countries. It gives us a country as well as a female percentage and a male percentage who are literate in each of them. The first stem plot that we're going to construct will just deal with the female percentages. The second will do a comparison of female and male. Since we're just going to focus on the females for our first stem plot, I want you to look at the type of numbers that we have in our data. Because these are all percentages rounded to the nearest whole number, we are going to separate them into the stems and leaves by the ones place and the tens place. So I'm going to look first at that tens place and see what my smallest value is. And it looks like it's a 2 down here at Yemen. Next, I'll look for the largest value in the tens place, and it appears that 9 is as high as those values go. So I know that my stems need to range from 2 to 9. So I've used those values, 2 to 9, to put in my leftmost column. Those are my stems. And what I do to fill in the leaves is I start looking through the table. Oftentimes I like to go in order, so I look for all of the data values that start with a 2. If you look at the table right above in your notes, you can see that the only one is Yemen, and its ones place is a 9. So that means the only leaf that I'll have next to the 2 is a 9, because there's only one country that has a literacy rate for females in the 20% to 29%. So moving on, I'll look at the 30%. I see that Bangladesh at 31%, and I see Morocco is at 38%. So I'm going to need to put in a 1 and an 8 as leaves on the stem of 3, and I will always put those in numerical order. One thing I should mention here is that we want the stem plots to abide by the area principle that we've talked about previously in class. So I don't want to, I want to kind of space the numbers out well enough so that the 1 and the 9 kind of take up the same amount of space. If I move this rectangle here, you can see that I filled in the rest of the stem plot. So we have one country that had 46% literacy, that was Egypt. We didn't have any countries with 50% literacy, or rather anything from 50, 51, all the way up to 59. So I do leave the space next to 5 blank. I don't omit the 5, I still need to write it there to show that there's a bit of a gap in the data. You can probably follow along with the rest of these and see where they came from. For example, Lebanon would be 82%, and Malaysia would be 85%, and so forth and so on. So you not only want to be able to construct a stem plot, but also read it and kind of pair it back to the original data that it came from. In your notes packet, I've asked you to describe what you see, and I have an example here that describes really just the shape of this distribution. So it doesn't include center and spread as a full description should for any numerical graph. So like I said, I just wanted to kind of highlight that this is one way I could kind of talk about the shape. In terms of the center and the spread, I would need to do calculations for that. So because the shape of this graph is not all that symmetric, we would probably use the median and either the range or the IQR to describe the spread in this case. As I mentioned earlier, stem plots can be used to compare related sets, that is, two related sets in a back-to-back stem plot. So what we've done here is we've taken that stem plot that we just constructed on the last page, the female literacy rates in Islamic countries, and we've kind of flipped it over the stems, kind of, a reflection here. So this 2 and 9 still represents 29%. So we'll always still read out from the stems to the leaves, 31%, 38%, 46%. Of course, I could have left them on the side they were and added the males onto that left side of the graph, but this is just how I happened to construct this one. So the males did not have any literacy rates from 20 to 29 or 30 to 39, nothing in the 40s. You can see that I've filled in, if you look back at that original table, filled in the leaves for the values that they have, and I did need to add a stem of 10 in order to fulfill the 100% for 3 different countries. So I want you to notice that it's okay that our stems have more than one digit, but a leaf can never be more than one digit. So in those original directions, it talked about separating the stems and leaves by basically just taking off the rightmost value. Those will be your leaves. Everything else will be the stem. If you're ever asked to compare two sets, you want to compare their shape, centers, and spread. And then you might also include a statement like this that says, we can see that literacy is generally higher among males than among females in these particular countries. I've already warned you about stem plots abiding by the area principle. We want to make sure, especially with ones, that they don't get so smushed together that a certain kind of series of leaves with a lot of ones in it doesn't look kind of more condensed than something with other, the same amount of other numbers in it. So just kind of keep that in mind. Also, stem plots don't work well for large data sets where each stem has to hold a large number of leaves. There is a modification for this. It's called splitting stems. And then another modification that helps when numbers are very large is called trimming. We're going to look at 2 examples from your book on how this works. But actually, first I'll do just a pretty easy one on splitting stems. So here it is. In this problem, we're looking at the number of hours random Bloomfield Hills High School students claim to have thought about math yesterday. If you look at the kind of data values we have some leading zeros. It looks like some people must have reported values here in like 10 hours or 12 hours. Here looks like 21 hours. That person's quite a suck up. Here we have 44. That clearly is an error. But I want to mention a couple things here. So we have leading zeros because we have some values in the tens and then some values that are just singles. So we put zeros in front of them. This value here would be 0, 9, representing 9 hours. You'll also notice that we have 2 different categories with zeros, 2 with 1s, 2s, 3s, and 4s. So that's really specifically what splitting stems is. If you notice, the zeros would have a lot of digits following them if we put them all together. So whenever we're going to have a lot of leaves, so a very kind of long branch there, so to speak, we might want to split the stems into sets of 2, or we could do sets of 5. Reason being, when we look at the leaves are always going to be digits. So leaves can only be one value, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And so that's 10 things, and the only factors of 10 besides 1 and 10 are 2 and 5. So we've split these into 2s. This first 0 will hold all of the leaves from 0 to 4, because that's 5 things. The second 0 will hold all of the values from 5 up to 9, because that's 5 things as well. Now, if you split stems in one spot, you have to split stems in all of the spots. So even though there wouldn't be quite as many leaves on the 1s or the 2s, we still split them for consistency's sake. So you'll notice that this first one here for the stem holds 0, 1s, 2s. It would hold up to 4 if anyone had reported 13 or 14 hours. The next one holds the only 15, but it would hold anything up to 19. And the same is true for the others. Again, we have some gaps here. We want to show that there are breaks in that data set, so you wouldn't discount these stems in your plot. So this is an example of how you split them into 2s. If you split them into 5s, then instead of having 5 options for your leaves, you would only have 2. So you would have a value that holds the 0s and 1s. You would have a stem that holds the 2s and 3s, another that holds the 4s and 5s, and so forth and so on. If we have really large data values that we're working with, things in the thousands, 10,000s and above, or really small values that incorporate a lot of decimal places, we might trim and use a leaf unit in our stem plots to help kind of simplify the data. In the math world, we're going to call this truncating. It's different from rounding. If we're going to truncate a number, we would take something like 8,576 and just call that 8,000. So again, it's different from rounding because we know 8,576 would round to 9,000 if we were rounding to the nearest thousand. So truncating kind of just chops off these last values, makes them a bunch of zeros, and then we can drop the zeros when we make our stem plot so that it's a little bit easier to read. This is going to make more sense once you take a minute to pause the video, turn to page 44 in your book, read through example 1.5 on Virginia college tuition, and I'm going to talk through the table of data as well as the stem plot once you resume the video. This table, which is on page 45 of your textbook, shows the tuition and fees at Virginia colleges and universities for the 2005-2006 school year, so a while ago. What this table doesn't include are the 23 two-year community colleges that each charge $2,135 a year, as was mentioned in the reading that you just did in example 1.5. So be aware of that. They weren't going to list the 23 community colleges that all have those same values, but those are going to show up in our stem plots. So we're looking at this data. We can see that it's pretty specific, and here's where we're going to truncate the numbers before we create our stem plot. So just to give you an example, Richmond here is at $34,850. When we go to create our stem plot, we're just going to call that basically $34,000. And then it will work similarly for the rest of them. So if I look here at, let's see, Virginia State, $11,462, we'll just call that $11,000. So here's a stem plot that Minitab, which is statistical software, made for the Virginia tuition rates. I want you to ignore this column for a minute. Pretend it's not there. I'll address it eventually. and I want you to imagine the bar is drawn here. The software just doesn't do that for us. So now it's kind of looking a little bit more like one of the stem plots that we've already addressed. The next thing I'd like you to look at are the stems. So we can see that the stems have been split because they repeat. There are 4 zeros here. There are 5 ones, 5 twos, and 3 threes. So these stems have been split into 5s. While we don't have 5 zeros or 5 threes, that just means there weren't any values to put into a 0 that would have gone up here, or the 2 other 3s that would be below there. So the only ones that are omitted are if there aren't any data values on the ends to put in those spots. But we didn't omit any of the 1s or 2s, so that, again, we can show kind of how spread out the distribution is. So this first 0 that's listed up here, the one that I wrote in, that would have leaves of 0 and 1. The second 0 has leaves of 2, and it would have 3s if there were any, 4 5s, 6 7s, 8s, and 9s. So there's one value, or one leaf that has a value of 9. And then it works the same for the others. So 0s, 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, and then we move on to the 2s, and we have 0s and 1s, 2s and 3s, and so forth and so on. The next thing I want you to notice is that we have a leaf unit up here. Typically, if we truncate values because they are large, we want to be able to, take something like 8,576, call it 8,000, and then drop the 3 zeros at the end. So we create a leaf unit to kind of simplify the visual here. So let's look at this 2 and 5 here. The leaf is the 5. The 5 has a unit of 1,000. So that 5 represents 5,000. And then the 2 as the stem goes to the left of that. So this data point actually represents 25,000. And that 25,000 represents a college or university listed in the table, again on page 45, that has a tuition of 25,000 and something. And if you start to search through that table, you'll see that almost at the very end, Washington and Lee has a tuition of 25,760. So this stem and leaf is what represents that particular university. Similarly, if we look at another row here, we have the first row of 1s, which has leaves of 0s and 1s. This row means we have a university in the 10,000s and another in the 11,000. And if you look at the table, you'll find that Bluefield and Virginia State must be those 2 universities. Let's talk about this row here, and then I'll get to this green part that I know you've been wondering about. So these values are not represented in the table. These are actually the 23 community colleges that were discussed in the wording of the problem. So following the same format, the 2s being in the thousands place would mean they represent 2,000. A leading 0 just doesn't do anything for us. It just tells us that, we have 2,000. And we have 2,000 23 times. It's a pretty long branch there, but we've already split the stems as much as we could. So again, this is the 23 community colleges that are $2,135 each year. So lastly, let's talk about this green circled column that I told you to ignore. anytime statistical software makes a stem plot for you, it will include these values, which are really helping us find the median of this plot without having to enter it into our calculator and look at our one-bar stats. So it's giving a running total working from either end all the way into the middle, and tells us where the median falls. I want to correct before I go any further one mistake that's made. This value should be a 26 here. Okay, so this 23 is telling us there are 23 values represented in this row. The next is a 23 because there weren't any leaves next to the second zero, so we still have 23 values so far. And we still have 23 values so far in the next one. And then here, the row that says 24, we had another value tacked on, which is why it's moved up by 1. And this next one should be a 26 because there are 2 more values added there. We're doing the same thing working from the bottom. So we've got one university in the 34,000s. We still have 1 so far when we start moving up because we have all of these blank spaces. Now we have 2 at the 25,000. There are 5 data values in the next row, so we have 7, and so forth and so on. Up at the top here, we have n equals 60. For us, that tells us there are 60 values in this table. So we know since it's an even number, we're going to have to average 2 values together to get the median. But instead of having to do all of the counting ourselves, they've done some of it for us. So if we continue on after 26, notice the next row has this 5 in parentheses. That tells us we know that the median falls in here. To find exactly where it is, that's the only place that you need to do any counting. So if we have 26 values so far, this 2 would be 27, 28, 29. And then if I notice kind of jumping down a row, we had 29 values so far. So this 3 would be 30, as well as the 2 would be 30. Coming from the other direction. So 30 values above, 30 values below, we're going to average those two together. So if I come down here, the 2 is really 12,000. The 3 is really 13,000. So that tells us our median is about 12,500. It's not going to be perfect since we had truncated these values, but it gives us a good idea of where the median falls. Lastly, we need to talk about dot plots, and I'll do so very briefly. I'm actually going to show you one more stem plot and a dot plot that corresponds to it because they're really straightforward. They're easy to create, they're easy to read. Dot plots use a horizontal axis labeled with numerical values, and it puts a dot in a vertical column above the appropriate value. So it's similar to a bar graph, but it's using dots instead of a bar, and a bar graph is only used for categorical data where we use a dot plot for numerical data. The next slide is going to refer to page 47. We're going to talk about cheese and chemistry. So here we are. If you're following along in your book, you'll see that there is some text above this table here if you want to pause the video and go ahead and read that. I'm actually going to go through the stem plot first since we were just talking about those. If you look at these data values, we have lots of decimals here. And so we're going to have another leaf unit, but now we'll work in the opposite direction. We'll look at how a leaf unit makes things smaller rather than bigger in the last example. Again, you'll see the median counts helping us here. We know that the median will fall in this row with the parentheses, and we've got 30 values, so just similar things to notice. All I'm going to do in this one is kind of highlight this first value, so here's where our vertical line would be. This first value, and make sure you understand how to read it with the leaf unit. So these leaf units, it tells us that we have, each leaf will be in the hundredths place. So I'm going to go ahead and put a decimal and 2 spaces, because this one would be the hundredths. So that's where any leaf is going to go. So the 6 goes there, and then I fill in the stem right before that. So the 8 would go there. So you can see that 0.86 is our first data value listed here. It's also the first one listed on the table. Just to give you one more example, if we move down to a stem of 18 and a leaf of 1, we would have our decimal, our 2 places, the 1 as the leaf goes in the hundredth spot, and then 18 fills in before that. So here's the 8, here's the 1. So this value is 1.81. So let's shift over here and look at the dot plot. You can see again, the horizontal line has the numeric values on it. It doesn't give us a whole lot of detail, so it's not like it lists every single value, and it has dots above where the specific data points would fall. So I think that that's probably sufficient for a dot plot. That's all I have for you in this video. As kind of a summary behind stem plots and dot plots. Remember that you can always do some more reading in your book if you are still confused.